In my previous video, I showed you how to connect to a Postgres database in Go using SQLX and PQ. We also created a database to store user data. Today, I would like to build on that foundation to implement password authentication using Argon2. If you have watched my previous video, you can pick up where we left off, but if you haven't, it's also fine. There is the GitHub repo in the description below, and you can use it as a starting point. First, we need to understand how password hashing algorithms work. This is Bob. Bob wants to create an account on our website with videos about programming. He inputs his email address and a password. We need to transform his password in such a way that we can, at any time, check if his password is correct. However, we also need to make sure that the bad guys won't be able to easily guess his password just by looking at the encrypted form. This is why password hashing algorithms were invented. We take Bob's password, mix it together with a random value called salt, and apply some sort of complex and slow computations, ending up with a string that looks like this. This string contains an identifier of the hashing algorithm, its parameters, the salting value, and the result of all those computations. Whenever Bob wants to sign in, we take his password, add the salt, and apply the same computations. If we end up with the same value, it means that the password is correct and that we can let Bob into the system. In this video, we are going to be using a password hashing library called Argon2id. Let's start by installing this library. Open a terminal and cd into the directory for the Goma project that we started in the previous video. On the website of a package, click on the clipboard icon to copy the import path to the system clipboard. Then in the terminal type go get space, then paste the import path and press enter. Using mkdir-p, create a directory at exp/argon, and inside that directory, create a file named main.go and open it in a code editor. The exp part stands for experimental, because we are going to write a smaller program before integrating the password hashing algorithm into the bigger system. In this file, define package main and func main. Inside main, we define a password variable, then create a new password hash based on the plaintext password and default hashing parameters. If any error occurred during the hashing process, we log the error and exit, otherwise we print the hashed password. Next, we try out a few passwords to see if they match. For each password, we run the check, and if it raises any errors, we log the error to the standard output and exit. Otherwise, we print the tested password and the result of the check. When you run this program, you should see a password hash string printed to the terminal. Below that, we see all the passwords that it tested. As we can see, only the original password matches the test. If you run the program several times, you may notice that the password digest is different every time. This is because of the random salting value. This algorithm is designed in this way so that in case of a database breach, breaking one password hash would not compromise other accounts. First, let me quickly explain the project structure we are going to implement. In this video, we are not working with a framework, so there is no one true project structure. We will be writing a store containing the logic responsible for simple database interactions. On top of the store, we will implement a service which will handle the more complex logic, such as the password authentication workflow that we are going to implement today. The controllers and views are out of the scope of this video. Let's start by defining a user type. Back in the root directory of the project, create a directory called types. Inside this directory, create a file named user.go and open it in a code editor. Start by defining the package name, then define a user struct. We need to map every column in the database table to a field on the struct. For the ID column, we define a struct field called ID with 2 capital letters. Every column in the struct must start with a capital letter, otherwise SQLX won't be able to map the columns to the respective struct fields. Since the struct field name is different from the column name in the database, we need to add an annotation after the field type to tell SQLX to match this field to the ID column. Then we do a similar thing for email. For the password hash column, we need to define the struct field as a string pointer. This is because the corresponding database column does not have a not null constraint. With a pointer type, SQLX can map null values to null pointers. If we used a regular value type, trying to scan a null value would result in a runtime exception. For the remaining 2 columns, we use time.time. This is the default data type for dates and times in the Go standard library. Now that we have the user struct defined, let's build a store. In this setup, the store module should define operations interacting directly with the persistence layer, such as inserting, reading, or deleting data. For the more advanced use cases, such as data validation or password hashing, we will later define another module called a service. In the root directory of the project, create a directory called store. Inside this directory, create a file named userstore.go and open it in the code editor. Start by defining the package name, then define a struct called UserStore. This struct will only have one field called db, where we can store a pointer to a SQLX database connection. By keeping our own database connection within the store struct, we can write unit tests connecting to a dedicated testing database. Define an exported function called new UserStore that accepts a database connection and returns a UserStore struct. Within the function body, return a UserStore struct with the same database connection. Since the DB field on the struct is private, only functions within the same package can set this field, and that's why we need to define a constructor function. Define an exported method called InsertUser on the UserStore type. This method accepts a pointer to a user struct and returns a pointer to a user struct and an error. In this method, first define a variable to store the result of a SQL query. Then, using the get method on the database connection, run this insert query and scan the returned data into the result variable. In the case of the users table, the only two columns that we need to provide are email and password hash, and for everything else we can rely on the values generated by the database. Therefore, we define two placeholders in the SQL syntax, and we pass the values of email and password hash as parameters. Since we added a returning asterisk close to the query, the database will return all columns of the newly inserted record. If any error occurred, we return nil and the wrapped error message. Otherwise, we return a pointer to the result variable and a nil error. At this point, we have a function that looks like it should work correctly, but we have no user interface to check if it works. Let's write some unit tests instead. Some people will likely argue that a unit test should never touch a real database, and that a test talking to a database is really an integration test, but honestly I don't care. First, we're going to need a database, and we will have to run migrations on the database. As this is a task we will have to perform many times in the future, it makes sense to write it as a make target so we can have it automated. Since I'm working on Debian, the make on my system will be GNU make. If you are on macOS or on a BSD system, the default make on your system may be BSD make, in which case you may have to install GNU make separately and run all make commands as gmake. In the root directory of the project, create a file named Makefile with the first letter capitalized and open it in a text editor. Now we are going to define a target called dbtestprepare. First, type the name of the target followed by a colon. The following lines will contain instructions and must be indented with one tab. Create the test database and ignore any errors. This is the most concise way of creating a database, only if it doesn't exist. Then run migrations using Goose app, passing the test database URL variable to Goose as the connection string. The @ sign at the beginning of the line instructs make not to print the command before it is executed. Now in this target we are referencing two environment variables, one for the database name and another one for the connection string. We need to make sure that both variables are set before we do anything. To this end we can implement a guard. Add a target called guard-%, and inside add this scary looking command. Now what test-n does is simply check if its argument is a non-empty string, and if this command fails, we print a nice error message with echo and exit with a non-zero exit code. Now add these two guards as dependencies of a dbtestprepare target. If you try to run make dbtestprepare now, you will get an error message because neither environment variable is defined. Let's set these variables by adding them to our .envrc file. Set test database name to goma_test, then set test database URL to a connection string for this database. Do note that the expression on the screen uses variable interpolation rather than a hard-coded name. If you have configured drenv correctly, when you save this file and open a new shell, you should see an error message asking you to run drenv allow. If you don't use drenv, you can set the correct environment variables by sourcing this file. When you write make dbtestprepare now, it should correctly create a database and run migrations. You can verify this by connecting to the database and seeing its schema. In the tests, we are going to use a library called testify to improve our testing experience. On the website of the testify package in the Go package registry, copy the import path of testify into the system clipboard. In the root directory of the project, install the package using go-get, pasting the import path. Now, inside the store directory, create a file called StoreTest.go and open it in a text editor. First, define the package name. Since this is a test file and the directory name is store, the package must be named store_test. In this package, just like in main.go, we are going to have to import pq, prefixed with an underscore. This is necessary in order to connect to a Postgres database using SQLX. Then we are going to define a test suite. This is a feature of a testify package. First, define a struct type called StoreTestSuite, embedding the suite.suite type from the testify library, and then add an unexported field called db, which we are going to use to store a connection to the test database. We can share this setup for all tests inside this package. Then define a method called setupTest on this type. Inside, fetch the connection string for a test database from the environment. Connect to the database using must connect and store a pointer to the connection in the db field. Finally, execute this query to empty the users table so that we can start each test run with an empty database. In order for the Go test runner to execute this test suite, we need to define a regular Go test example. Inside this function, we run suite.run with a t parameter provided by the test runner and a newly initialized StoreTestSuite struct. Next, let's define some test examples for a UserStore. Inside the store directory, create a file named UserStoreTest.go and open it in a code editor. Start by declaring the package name, which is store_test. Then define a test example as a method called testinsertuser on the StoreTestSuite type. In this example, we are going to test if the store can persist a user in the database when called with valid parameters. First, we need to declare the password hash as a separate variable. This is because the password hash field on the user struct is a pointer type, and we can only obtain a pointer to a string if it is stored in a variable. Then we can instantiate a user struct with an example email and a reference to the password hash variable. Then construct a user store with a test database connection. Finally, we can call InsertUser with a reference to the user struct. Then ensure no error was returned and assert that the ID field of the result is greater than 0. Since the ID column is generated by the database, checking if the field is non-zero is a good way to ensure that the value has been correctly saved. Then we can check that the email address and the password hash have the same values as the ones we have passed to InsertUser. We can run the tests for the whole project using the command go test-v./3. However, we can save ourselves some typing by defining a make target to run the tests for us. In the Makefile, define a target called test with a dependency on db.test.prepare. Then add the command to run tests. Now when we run make test, the command should prepare the test database and run all tests. We see that all examples should be passing. Now let's improve our tests by also testing the user count. When we insert a user into the database, the user count should change by 1, so we can query the user count before and after the call to InsertUser. In the UserStoreTest.go file, define a function called countUsers that takes a database connection and returns an integer and an error. Inside this function, define an integer variable to store the result of the count query. Then run this SQL query to count all rows in the users table and scan the return value into the result variable. Finally, return the result and the error returned by scan. In the test example, call this function to count users before the call to InsertUser and ensure that no error was returned. Then do the same thing after the call. Finally, add an assertion to check that the count of users after the call to InsertUser is equal to the initial count plus 1. Do note that in the call to equal, the first argument is the expected value and the second one is the actual value. If you run make test now, all the examples should still be passing. Before we can implement the actual user authentication, we are going to need a way to retrieve a user from the database by their email address. Open the UserStore.go file. Let's begin by defining a method called getUserByEmail on the UserStore struct that takes an email address and returns a pointer to a user struct and an error. Inside this method, define a variable to store the result of a SQL query. Then, query the database and scan the return value into the result variable. The SQL syntax contains a placeholder for the email address, so we also need to pass the email address as a parameter to the get method. If the operation returned an error, we return nil and wrap the error. Otherwise, we return a reference to the result variable and a nil error. Now, let's test if getUserByEmail works correctly. In the UserStoreTest.go file, add a test example called test_getUserByEmail. First, we insert a user into the database. We define the parameters for a new user, insert them into the database, and check that no error was returned. Start by testing the happy path. Define a slice of strings with email addresses that we want to test. All of these are variants of the same email address, just with different capitalization. Since the email column in the users table is case insensitive, querying for all of these should return the same user record. For each address in this slice, we query the database with getUserByEmail, check that there was no error, and finally we assert that the returned user has the same ID as the record we are looking for. Then we query the database with another email address. The query will return an error, so we check if the return error wraps error no rows, which is what the database should return if nothing was returned from a query. Finally, assert that the return user record is a nil pointer. Now, if you run make test, all the examples should still be passing. Now we can implement a method on the users struct to check password attempts. Open the file user.go in the types directory in a code editor. Let's start by thinking about all the things that can go wrong. The first thing that can happen is that the user record doesn't have a password hash set, or that the column has an invalid value. You may think that it doesn't make too much sense to create users without passwords, but in reality there are some cases when these can be useful. For instance, sometimes you only want to allow a user to access your system with an API key, or for automated workflows like background jobs running on a fixed schedule. Another error that we can think of is when the password entered by the user is incorrect. For both of these cases, let's define error types using the function errors.new. Then define a method called CheckPassword on the user struct, taking a password as a string and returning a boolean and an error. Start with the happy path. If everything is correct, return true and a nil error. If the password hash field is nil or doesn't begin with the prefix for Argon2id, return false and the error no password set error. Then run the proper password check. If the check returns an error, return false and wrap the error. If the password is incorrect, return false and the error invalid password error. Now let's implement a user service. In this setup, a service acts as a link between a store and a request handler. Create a directory called service in the root directory of the project. Within this directory, create a file named UserService.go and open it in a code editor. Start by defining the package name. Then define a struct called UserService with a private field called store, which will hold a UserStore. Define a function called newUserService, taking a pointer to a database connection and returning a UserService struct. In this function, return a UserService struct with a UserStore, initialized with the given database connection. This will be our constructor that we will use to initialize UserService structs. Then define a method called AuthenticateUserByEmailPassword that takes an email and a password and returns a pointer to a user struct and an error. First, fetch a user record by the email address. If this operation returns an error, return nil and the error. Then check the password by calling the CheckPassword method we have just implemented. If a password check returns an error, return nil and the error. Finally, if this check has passed, it means that the user exists and that the password is correct. We can return the user and no error. Now let us write some tests for the user service. We're going to have to create a file named servicetest.go in the service directory. This file will be almost exactly the same as the one for the store package, so I'm not going to bother writing it out by hand. Instead, I am going to use a command line tool called sed. This command will read the file StoreTest.go, replace every occurrence of store with service, and print the result to the standard output. I pipe it to a command called t, which will also write the text to the file I passed as its argument. As we can see, this gave us a new struct type for the test suite and a Go test example. Now create a file called UserServiceTest.go in the service directory and open it in a code editor. Define a test example called test authenticate user by email password on the ServiceTestSuite struct. Start by inserting test data into the database. First, define a password variable and hash it using Argon2id using the default parameters. Assert that the createHash function did not return an error. Then define a user struct with a unique email address and the password hash we have just generated. initialize a UserStore and insert the user struct into the database, then ensure that no error was returned. Now we can test the actual function starting with a happy path. Initialize a user service with a database connection, then call AuthenticateUser by email password with the correct email and password. Ensure that no error was returned and assert that the user struct returned by the method call has the same ID as the user we have created. Then, if we pass the correct email and an invalid password, we should get a nil user and an error invalid password. If we pass a non-existent email address and the original user's password, we should get a nil and an error no rows. Finally, run this SQL code to update the password hash of the original user to an invalid value. If we try to authenticate with the correct email and password, we should get a nil user and an error no password set error. If you run make test now, all tests should still be passing. This is the end of part 2. It's been a long video, so congratulations if you made it this far. We have managed to implement a few functions related to database operations and password hashing. In the next video, we can take this knowledge further and implement user registration and login views. If you enjoyed this video, kindly give me a thumbs up. It really helps with the YouTube algorithm. If you are feeling very generous, please consider subscribing to my channel so I can become rich and famous. I hope you learned something and see you in the next one.